Hi, everyone. Thanks for joining. My name's Steve Kearns, and I'm the product lead for the Elastic Stack. And I'm very excited to be here to talk with you about the 7.0 release. I'm joined today by Clint Gormley, the team lead of the Elastic Stack, and we'll be talking a bit about the release at a higher level. What did we accomplish? How did we get here? How does this set us up for the future? And then we'll have a number of feature deep dives with the engineers who actually wrote the features themselves. We'll hear from Dave Snyder, the Kibana design team lead, Jim Frenzy on the Elasticsearch engineering team, as well as Yannick and Jason about cluster resiliency and scale, and then Thomas and Nick on the wonderful work we've been doing on the geo side of things. But before we dive deep into the details of the specific features, I wanted to step back for a minute and reflect a bit on the 7.0 release overall. If you've been following Elastic for pretty much any amount of time, I suspect you've noticed that we move fairly quickly. And 7.0 is quite a release. 10,000 pull requests represents a tremendous effort from more than 850 contributors. And the number of contributors is actually something we're really proud of. It's 861. We employ hundreds of engineers that wake up every day and work hard to move all of our projects and products forward. Really help make our users and customers successful. That's what we focus on. We try to do this in a very open way, and we really welcome and encourage and are so thrilled when we have the contributions and engagement from our community. So if you're one of the 861 people who created a pull request that went into 7.0, thank you. And your community extends beyond just people making pull requests, right? If you've commented on or plus one or created issues in GitHub, or asked or answered questions on our forums, or you've spoken at a meetup, thank you as well. Your contribution and participation is really what drives us and what it inspires us to continue to build as we go forward. One of the other impressive stats, I think, in the release here is the sheer number of release artifacts. That's 205 different binaries that we build, test, and ship with every release now. From an MSI for Windows, RPM zip files, and even Docker images for each of our products across all of our supported operating systems is quite a bit. Perhaps just as impressive is the fact that we support every Stack version in Elastic Cloud on day one. For those that aren't aware, Elastic Cloud is our hosted managed Elasticsearch service. And to get to the point where we're able to support all of these platforms and all of these products without slowing down our development, we've really been putting in the time all along to build the right infrastructure to help us scale in this way. I think a lot of this started, or at least became visible, back in 2016 when we first released 5.0. This is when we committed to releasing all of the components of the stack together with consistent version numbering. This is a huge undertaking, and over the years, we've built some of the most sophisticated testing infrastructure that I've ever seen, from automated CI tests to ensure changes in Elasticsearch don't have a negative impact in Kibana or properly accounted for, and then some really impressive automated randomized testing for Elasticsearch itself, where we do things like simulate network latency, partitions, and so on. And the reason that we do this is because it's our goal to be there for you wherever and however you want to run and use the stack. Now, Clint, I'd love to have you share some of your thoughts and perspective on the release. For those of you who don't know Clint, he has the distinction, you might call it foresight, or you might also call it a high risk tolerance, but he was the very first user of Elasticsearch way back in 2010, and was one of the first people to join the company in 2012. So he's been deeply involved since the beginning. Clint, over to you. How do you summarize or think about a release with more than 10,000 pull requests?
Well, a lot of those pull requests represent features which have already landed in the 6.x series. You may have seen some of the minor releases which we've put out have been so jam-packed with features that they feel like major releases. In 6.7, which just came out recently, we released GA versions of index lifecycle management, cross-cluster replication, frozen indices for cheap long-term storage, our Elastic SQL interface with JDBC and ODBC drivers, and Canvas, which is like a Keynote or PowerPoint for Kibana. That's huge. But we wanted to make those new features available to our users as soon as possible, instead of having them to upgrade to the next major version before they could start using them. Doesn't mean 7.0 is small. 7.0 has got some very big features in it. We've taken advantage of this major version bump to swap in new and improved versions of core features of the stack. Fundamental things like how search works and our cluster consistency model. These are really big changes. but they're just the start. These changes lay the groundwork for future improvements that we can build on top. This version of the Elastic Stack looks very different from our early releases. It's a much more mature product. We've had 7 years now to learn and grow. But really, we're still focusing on the same 3 principles that have made Elastic popular from the beginning: speed, scale, and relevance. We've always tried to make Elasticsearch easy to scale. It should be a system which works in the same way on your laptop as in a data center with 1,000 nodes. And we want to do it with the minimum of configuration or setup. Turns out this is quite hard to do. And in the early days, we didn't have a great story here. Disk corruptions went undetected. Clusters would silently enter split brains and lose data. There could be inconsistencies between shards, and so on. From version 1.4 onwards, we have made incremental changes which have really improved our resiliency story. We started with things like hashing files so that we could detect corruption on disk, and fixing some of the most obvious replication and cluster consistency bugs. Then we went on to redesign the underlying systems. There were a number of people out there who said, why don't you just use Raft or Paxos and so on? Which is easy to say, but it turns out that those models don't work so well with a system like Elasticsearch. So we had to go and write our own, adapting these existing models into something which works for us. But we didn't leave it there. These new models are formally proven and well tested, so we can be sure that they do exactly what they're supposed to do. So the first big change in consistency came with our document replication system. Previously, we used to transfer segments backwards and forwards, and that's how we kept shards in sync. In the 5 and 6 series, we introduced a concept called sequence IDs, and they were used to track which documents have or have not been replicated to other shards in a group. This allows us to safely recover from the loss of a primary shard and ensure that the new primary and any replicas contain the same data. As a nice side effect, it also made shard recovery after a disconnect much, much faster, as we just need to replay any differences between shards instead of having to copy over entire, potentially really big segments. Sequence IDs also laid the groundwork for a long-awaited feature which landed in 6.5 called cross-cluster replication. The ability for a cluster to replicate all the changes to an index from a remote cluster. Jason will be talking about cross-cluster replication later today. It will also enable us to add another long-awaited feature, the Changes API, where you can just follow the stream of changes as they come into an index. And we hope to see that during the 7.x series. The second big change in consistency landed in 7.0, and it completely rewrites how we manage cluster consistency. Anybody who's run an Elasticsearch cluster will be familiar with the minimum master node setting, which is used to prevent split brains. Unfortunately, they will probably also be familiar with how difficult it is to set this value correctly. But it was the price we had to pay to allow clusters to scale up and down dynamically. I'll leave it to Yannick to tell you all about how all of this changes in Elasticsearch 7. But with this rewrite in place, we can start to add new features like lightweight voting-only master nodes, which has also been a long-standing request. So with sequence IDs and the changes to cluster consistency in place, we have addressed the most important tasks listed on the Elasticsearch resiliency status page, meaning that version 7 is the safest, most flexible, easiest to use, and scalable version of Elasticsearch that we've ever delivered. So much about scale. We've also done a lot of work on speed and relevance. You know, a lot of the full text search functionality we use in Elasticsearch is based on theories that were first proposed in the 70s. And they've served us well. They do a really good job. Even BM25, which is the more modern relevance scoring function that we now use instead of TF-IDF, that dates from the 80s and 90s. So in 7.0, we have parachuted right into modernity and implemented something called BlockMax Weak AND, which was first proposed in 2011. I'll leave it to Jim to explain exactly what Weak AND is all about and how it works. But to put it simply, it greatly speeds up full text search performance at the cost of not telling you exactly how many documents matched. To me, this seems like a reasonable trade-off. Users are interested in the top 10 results, not the fact that 32,467 documents matched. That's more of a vanity thing for us to crow about. What the user wants to see is the right answers to their question. And the upside here is huge. The Lucene benchmark shows speedups of anywhere from 30% to 3,000%. But it's not just this performance improvement that matters. It's the other stuff that this change enables that's so important. For instance, it's no longer costly to search for stop words by default. And including them into the search means that we can both improve recall and precision. Search as you type using n-grams to sort of give you the prefix of words. Suddenly this becomes much more performant. And it means that we're going to be able to ship a dedicated autocomplete field out of the box in Elasticsearch that will just make this stuff easy. We have not implemented this feature in isolation. We've taken the function score query, which has always been used to include signals other than full text relevance, and we've replaced it with queries that understand how to use weak and while they're taking signals like recency or popularity into account. Of course, for all the logging users and other users out there, Elasticsearch is not just about full text search. Numbers, dates, geopoints, they're vitally important to the jobs we do today. And over the last few major versions, we have seen big speedups, but mostly by switching to using block KD trees for indexing these values instead of the inverted index. BKD trees are back in the news, and this time we've used them to improve geoshapes. Geoshapes were these slow, clunky, memory-hungry, inexact beasts. Using them with a precision better than about 10 kilometers was pretty much unusable. They were costly and slow. By contrast, the new implementation is accurate down to a millimeter, while being 60% faster to index, 60% smaller in disk, and 50% faster to query. One big geo user has reported back to us that they've seen a 25 times speed up for their use case. So Nick will be telling us all about the new geoshapes, and Thomas will demonstrate the beautiful new Kibana GIS app, which shipped in 6.7 and is currently in beta. Speaking of Kibana, Steve, I'll hand it back to you to tell us about some of the new Kibana features that shipped in 7.0.
That's great. Thanks, Clint. Yes, 7.0 is a pretty exciting release for Kibana. I think the most obvious change is the new design, and we'll be hearing from Dave Snyder, the Kibana design lead, about the thought process behind the new look, and just as importantly, how we ended up building it. But to me, I think a big part of Kibana 7 is about showcasing and embracing the expanded role that Kibana is now playing in the stack. If we look sort of back in time historically, Kibana's primary role has always been as a great way to visualize the data that's stored in Elasticsearch. And that's, the role is expanding, but that will always be something that we focus on in Kibana. But we're adding to that an increased focus on making Kibana a great place to manage the stack, a great place to monitor the stack. And increasingly, you're starting to see it's becoming a home for these sort of dedicated solution experiences. Now, I'll get into that a little bit more in a moment, but first on the management side of things, hopefully, if you've been following our more recent releases, you've seen as we've been adding new features to Elasticsearch, we of course are starting with a well-designed API and so forth, but at the same time, we're introducing these new features like rollups or cross-cluster replication. We're including management UIs as well. And I think that this is something that we're going to see a lot more of going forward. And we have a dedicated team working on management interfaces for Elasticsearch. And so going forward, the number of UIs that we have inside of Kibana to manage the stack will continue to get richer and richer over time. The other new role for Kibana that I mentioned is sort of a home for solutions. If I look backwards, for a long time, we sort of focused at Elastic exclusively on making the stack better for as many users as we possibly could. So we kept trying to expand what the stack is good at. If you go back 4 or 5 years, people started putting log data into the stack, and they said, hey, how do I get to 1 million events per second as in terms of an indexing throughput? And we said, oh, well, we can do something about that. And we went and we worked to make indexing a lot faster. Same thing as people started to do richer analytics in Kibana, and they started to say, well, gosh, we need to do things like a moving average, and we need these other calculations on the results. So we added pipeline aggregations and support for that into Kibana. But inevitably, this focus on broadening the stack and making sure at the base level we get better and better at the things that we do meant that we weren't focusing on some of the specialized or specific use cases. And it was this trade-off between, if we had spent a ton of time focusing and being a logging solution, we wouldn't have been able to go and build some of these other great things, in fact, many of which we'll be talking about today. But as we grew as a community, as we grew as a company, we've reached the size where now we don't just feel the weight of trying to do the right thing for all of our users and all of you out there who are using us for a specific use case. We have to. It's the right thing for us to do, is to focus on both the core and the specific use cases. And so what we've started to do, and you can start to see this now in Kibana with the APM application, the infrastructure UI, the logging UI, and now maps as well, you can start to see us taking a much more focused approach to some of these solutions with dedicated engineering teams behind them. And so these UIs that you see, you can think of them as the tip of the iceberg of the solution work that we're doing in these areas. And we'll do deep dives on our thoughts on APM and logging and metrics with other webinars and other blogs. But I mention it because it's starting to change the way that we build Kibana and the way that we think about Kibana going forward. We're starting to think of all of the features within Kibana as a set of services, a set of sort of layered services from UI reusable components, charting libraries, and everything right down to how we query Elasticsearch as this set of services. And so instead of building Discover or Dashboard and Visualize as its own sort of single application, built just for itself, we're thinking of actually building those as a set of services into the platform that those applications just come and consume. And that means that other solutions that like the ones I mentioned and more into the future, that these solutions will be able to capitalize on those services that Kibana is building. So this starts on the front end, and Dave will talk about that. But it's worth noting that this also extends all the way through the back end of Kibana as well. And we'll see a lot more on that over time. Finally, I wanted to mention a few things we've done on the ingest side of the house. One of the big ones that you see in 7.0 is what we call the Elastic Common Schema. This is, you can think of it as a consistent way to map similar data into a consistent set of fields into Elasticsearch. And this is really important because as we see a lot of our users taking data from different data sources that represent sort of the same thing in your environment, in any sort of company these days, you might have an Apache web server over there, Nginx over here, and the people using Windows have IIS. If I wanted to look at all of the web servers across my infrastructure, it's hard to do that if you've got the data stored in different fields for each one of those data sources. And so Elastic Common Schema gives you the structure into which to drop those. So what is the URI being requested? That goes here. What's the IP address making the request? Okay. What's the response code that we're sending back? Goes here. And having that consistency means you can build one dashboard, one chart that includes data of all of these different sources. So for 7.0, we've converted all of the modules that we produce over to using the Elastic Common Schema. And if you're not familiar with the concept of modules, we've been building these now for a couple of years. You can think of them as a pre-canned data source where we wrap up, if it's a log data source, for example, we wrap up where does the log file live, what kind of enrichment do we need to do on that log file, and then going from there, looking at what are the most efficient mappings for Elasticsearch, what is a dashboard that's a useful way to look at this data, and even including things like machine learning jobs and alerts right as part of the module definition itself. And so we've converted all of these modules that we've already created over to the Elastic Common Schema, and we're doubling down. I think if you were to look recently, we've been on a bit of a tear, introducing a whole bunch of new modules into the stack. Everything from auto-discovery support for Kubernetes and containers and pods that are going to be running in there, simplified Prometheus metrics integrations, and even security-centric data sources like Bro, Zeek, Suricata, and modules like for things like NetFlow, some pretty sophisticated data sources that we're integrating directly into the stack, directly into the Elastic Common Schema. Gosh, there's so much more that we could talk about here. Features that we've added to Elasticsearch, like adaptive replica selection to improve query consistency performance-wise, and avoid hotspots, or smarter defaults that improve indexing throughput, when you're not querying those indexes. But I think we need to now start to dive actually into some of the individual features. So first up is Dave Snyder, design team lead of Kibana, to talk about the Kibana 7 design and how there's much more to it than dark mode. Dave, over to you.
Thanks, Steve. My name is Dave Snyder. I am the Director of Product Design at Elastic, and I'll be talking about designing Kibana 7.0, which to me starts on my very first minute of my very first day at Elastic. I did what any tech employee would do, and I put out on Twitter, hey, I'm joining Elastic and working on Kibana. And within minutes, I got requests from users asking me to bring dark mode back. That's how you know you're joining a good company. I also, being a designer, it's really nice working in an open source company because you don't really have to go too far to figure out what people don't like about your product and what you need to improve on here. I very much remember an early ticket that was about improving the dashboard mobile experience. People wanted to be able to see these things on their phone, and that made obvious sense to me. And I'm happy that we were able to address that in 7. And of course, I'm a designer myself. I come into it and look at the product and say, some of these things look like they should be pretty easy to fix. Why why doesn't the screen work all that great? Why does this date picker push all this content down? And of course, you go in pretty naive, and it could be further from the truth. These things are actually extremely hard to fix. I'd like to just start at the end. We're going to go straight to a demo here of where we landed with Kibana 7 and talk through some of these features, and how we solve them. So pretty traditional dashboard. Looking at Kibana here, I've just got some sample data of sales stuff in here, and talking about that top area, that was one of the biggest things that we wanted to fix. So being able to have the screen resize and actually work in a consistent way. We're a big fan of getting Kibana out of the way. So that meant rethinking the way that we did our entire navigation, really minimalizing the UI here so that your focus is actually on the content within the screen. Everything that we did when we went through this design was thinking about ways to hide things. So for example, the date picker, which was always available in that top right area, it's still available in that top right area. But now it's a little bit more flexible and allows you to get to places fairly quick. But probably the most exciting thing that I'd imagine people have is, this dark mode. And the first thing to mention is it's completely space aware, and it works across Kibana completely. So here we are on Kibana's homepage. People may think of dashboards when they think of Kibana, but when I think of dark mode, I think of our logs UI. I remember working with Felix, one of the engineers at Elastic, on trying to think through, hey, what should this log system, look like? And to us, we thought it should really just be like a super terminal. And to me, we originally, saw that as something that was available in a black screen. I think of terminals, I think of dark screens. I don't think of a light mode. So, more than anything, I was really excited to see the dark mode available in this area, but it does go everywhere. So everything from our map system as well, where you can see all of our individual form controls are working perfectly. I can come in here and inspect things, but then to those dashboards as well, which we know is where Kibana sits. And a lot of times they're up on screens, sometimes with the lights off, and you want that dark mode available. I'm just loading some metric beat data here from my local machine, but you can see here that we've got everything working in dark mode in a pretty great way. And this same dashboard is available over here on my simulator. And that was another big thing that we wanted to do with the design of Kibana. So not only does it work on this big giant screen, it works over here. We'd still classify this as probably pretty beta. It's something that we're going to improve on as we move forward. But the navigation system, even those date pickers that we were showing, for example, I could start polling this mechanic and get everything working the way that we wanted. So, looking at this stuff, I just kind of want to go to how did we get here? You know, if you're looking at that screen, you're saying, hey, that's pretty simple. You know, it's got a dark mode. We moved some stuff around. That's great to me because on my side of it, there were a lot of dragons that we had to get by to get there. And the first one is always just our community. You know, you bring up people just hate change. If you change things too much, it's not going to be a fun experience, especially when you're using Kibana as a daily tool and it's something that you get familiar with. But, you know, as you make those changes, they all build up, you lose consistency. And to me, that's the heart of what a designer needs to think about. And so when we thought about how are we going to attack this design of Kibana, we started with some values. And to us, that's saying, look, everything needs to be accessible. And by accessibility, we mean color blindness. We mean screen reader support. You can tab around without using a mouse. We want Kibana to be as useful to everybody that's out there. And we wanted it to be themable. That meant that I never wanted to ever get a tweet about dark mode or pink mode or blue mode for Kibana ever again. Responsiveness. We did want it to actually work in those different screens. And, you know, as a designer, I want my designs to be playful. I want to have fun when I'm using an application. That means adding some light animations to places to just make it a little bit more fun. But most importantly for us as a distributed company and a company that's open source, our design really needs to be well documented. People are building plugins on top of Kibana. There's all kinds of stuff that's going on there. And we want it to be able, you know, getting to that service architecture that Steve mentioned, we want people to be able to just build what they want to build. And a lot of these things sort of led us to what we think of as our guiding principle with Kibana design, and that is to focus on the content first. That meant defocusing the Kibana application itself. When I, you know, started at Kibana over 2 years ago, we had the pretty famous large navigation here on this left side, which with a lot of color. That's immediately where your eye gets drawn, and your eye needs to get drawn to that graph and the content on that right side. So we had to say goodbye to that large pink blue nav. We hardly do you, but it made its way out. And really, we just need Kibana to get out of the way. So here, looking at our Maps application, what you need to realize when you're building an application like Kibana is you aren't building an application. Even as a tool builder, you're not using a tool, you are building a map. And the map needs to be the primary focus of what you see on the screen. And so when we think about design, what we're thinking about is how can we remove these things as you're, you know, trying to accomplish that goal. But getting back to the early days, how we sort of started this project, we did it the pretty traditional way that most companies would do things. We started in static mocks and we explored. We, you know, came up with new ideas on everything. We rethought how we did a lot of our visualizations. But after a couple months, we had a really big problem. A lot of this stuff, you know, looked great in our sketch files, but they actually weren't getting built. And we had a very big blocker that was there. And that was that Kibana itself was just growing way too fast. So if you look at the 6x cycle, the number of core apps, it more than doubled in Kibana's side nav. APM, infrastructure, logs, canvas, all during that cycle. And that meant that as a company, we were growing, we were adding more engineers, meant more teams were there. How do we keep these people consistent? You know, the biggest thing that we want to solve is that when you go from application to application, they all feel the same. And that's pretty hard when you're doing things that are varied as a mapping application, a logging application, or even something like ILM management with Elasticsearch. And, you know, just at the end of the day, our design code, it just couldn't keep up with that. It was brittle, to be honest, to start with. It meant that we would have to rewrite our entire CSS layer to get there, especially for something like theming. And, you know, when we came down to it, we realized we weren't working on a redesign. We were working on a design at scale problem. And we needed a way to sort of up our game there and make things consistent. And to solve that, we ended up building the Elastic UI framework. And whoop, like everything at Elastic, we of course open sourced it. So I'm just going to give you a brief demo there to show you what the Elastic UI framework is. We like to call it EUI, but it is basically a React and CSS library where we have documented the entirety of all the UI controls that we go to build out Kibana. So everything from card systems to, for example, I mentioned having quite a lot of difficulty thinking about date time systems. Look at the level of documentation that we take on something like this. When we look at that super date picker that exists within Kibana, we've got to think of every state. And not only that, we've got to provide a set of documentation from a code layer, both for our internal company, but for the community that says, this is the way that you can use these things. This is the way that you can build. So everything that we do from that nav drawer to these individual components, we document, we provide in EUI, and we release it rapidly and let all of our systems and various UIs use it. And that's just a little insight into how we went about scaling design at Elastic and building out that Kibana 7 system. We're really excited about it. It's a big change. We've been working on it for quite a while, but hopefully it's not too big of a jump for you and should feel fairly familiar. And with that, I'm going to pass it over to Jim, who's going to take us on a completely different topic into the realm of making Elasticsearch a lot faster.
Thanks, Deb. Hi, I'm Jim Ferenczi. I'm a software engineer here at Elastic, working on the search side of Elasticsearch. And today I'm going to present some of the main features that we added in Elasticsearch 7 to make search faster and hopefully easier. So a little word about the agenda for this session. So I will start with the things that we did to make search faster in Elasticsearch 7 and the trade-off that we had to make to allow this new order of magnitude when it comes to search. One small clarification here, when I talk about search, I'm talking about the process of retrieving the top document that match a query. So the idea here is to make this retrieval faster. So I'm not talking about aggregations or anything that relates to analytics. In the second part of this presentation, I will show one new field type that will be added in 7.1 that leverage the fact that we have faster search in 7.0, and that allows us to build a search as you type experience directly integrated into the Elasticsearch Query DSL. We will see how it works in a live demo. Then I will say a word or two on how to combine relevant signals efficiently in Elasticsearch 7. This is a topic that was difficult to get it right in previous version. So in Elasticsearch 7, we introduce a new field and a new query that allows to efficiently combine textual score with static signals like page rank, for instance, that are not related to the query, but related to the popularity of the document, regardless of the query. Finally, I will introduce a new new family of proximity query that we call intervals query that are based on clear semantics and with the goal of replacing span queries soon. So let's start with making search faster. So making things faster is one of the main challenges in engineering in general, but in the context of Elasticsearch and Lucene, this is even more challenging because we are talking about solutions that are quite mature and quite optimized already. So when we discussed this at the beginning of the implementation of new features for Elasticsearch 7, we tried to find new ways to think about search that would allow for significant improvement to the actual search. So one question we ask is, can we make search faster if we don't need the total hit count? So this is something that was limiting for a lot of versions of Elasticsearch. Every query that is run inside an Elasticsearch cluster has in its contract the fact that it needs to return the total hit counts that match the query. This is something we changed in version 5, when we introduced index sorting. So we introduced a new option to disable the total hit counts when the query can early terminate. So when the query sort matches the index sort, we have a way to speed up queries. But there is no advantage of disabling the hit counts when it comes to normal search, so normal queries where the index sort doesn't match the query sort. So we brainstormed this idea, and we discovered that there are already many ideas on this topic that involve searching, retrieving the top end faster if we don't need the total hit counts with a simple ID. If we don't need to visit every document that match the query to count the number of to count the total hit counts, then it should be possible to skip what we call the non-competitive documents. So since we only want the most relevant document in the top end, it should be possible to skip blocks or single documents that we know with prior knowledge of the data that cannot compete with the already visited document. So this idea is quite old, in fact, and it started in 2012 with an issue opened by Stefan Pohl, a software engineer interested in Lucene, that opened an issue talking about an algorithm that is called BlockMax score, where the idea is to add information at index time regarding the maximum score that terms can have on a blocks of document. And so the simple idea here is to add at index time this extra information so that we can leverage the information at query time to compute the maximum score that the terms can have, so that the terms that appear in the query can have, and compare this maximum score for the block with the current least competitive score that we have in the top documents. If this least relevant document has a score that is greater than the max score in the block that we are currently looking at, then there is a possibility to completely skip this block and go to the next block. So this is the main idea that was implemented in 2012, but at that point, Lucene wasn't ready to really manage such a big change, mainly for reasons regarding the accuracy of the top end. So we wanted to make sure that if we apply this kind of optimization, we still return the most relevant document as if we visited the total number of documents that match the query. So it needed a few more years for Lucene to enhance the scoring, to have the ability to revive this issue. So it was sometimes around last year that Adrien Grand and a few committers in Lucene and Elasticsearch revived the original issue of BlockMax score and implemented for Lucene 8 a solution that is now able, with the new version of Lucene, to, by default, skip competitive document when the total hit counts is not requested. Let me just show you the effect of this optimization in a small example. So for the sake of the demo, I indexed a dump of the English Wikipedia with approximately 5.6 million documents. So here I'm counting the total number of documents. So there are still use cases where it's important to be able to count the number of documents that match a query. The query is a match all. And I index everything with an Elasticsearch node that is complete with the default configuration. So I didn't change anything in the setting. I just have some custom similarity here, but I'm not using them. The mapping is also very simple, so it contains a lot of fields. But for the sake of the demo, I just need a few fields extracted from the full mapping. So here I just use a create timestamp, that is the date of the creation of the article, a page view that was merged with this dataset, and from another dump of the Wikimedia that gives the unique access per article for the last several years. Because this data is quite big, I just extracted the page view for last week, but you will see that it's more than enough for the sake of the demo. I also index a text field, so it's the content of the Wikipedia article and the title. So if I run a search in Elasticsearch 7, the first thing to notice is that the block max score is by default activated in version 7. So here I'm looking for all the documents that contain the term the, which is a stop word. So it's a query that we know is slow in previous version, and I'm just running it on Elasticsearch 7. So as you can see, I would not say that 14 milliseconds is slow for a query. It seems very, very fast. And the reason is because we apply the blocks max score optimization, so that we don't need to visit every document, but only the document that can enter the top N at any time of the collection. The first thing to notice here is that the total that is returned in the response still have a value, but here the value is just a lower bound of the total number of documents that can match the query. It's set to 10,000 because by default, every query in Elasticsearch starting in v7 will track the totalities accurately up to 10,000. If you have a query that match more than 10,000 documents, that's exactly the response that you will have. You will have the value, the number of documents that match the query in the value, and the relation will tell you how to interpret this number. So in this case, GTE means greater than or equal. So this is an easy query, only one term with the within a single field, so the text field. One thing to notice is that as soon as I ask for aggregation, the optimization cannot kick in. And the reason is simple, it's because the aggregation here needs to access needs to visit all the documents. So we automatically disable the optimization if we see that there is an aggregation in the process. And you see that the took time is much, much slower. So, of course, only improving stop word query is not the ultimate goal. So here is another query that is still a stop word, but this time I apply it on two fields, title and text. So title contains, of course, all the title of all the articles, and text is the big body of all the articles that are present in Elasticsearch. If I run this query, you can see that the took time is still fast. And if I run the same query with the argument to disable the optimization, which is track total hits set to true. So here I want to explicitly track the total hit. We can see that the took time is much larger because this time to compute the top N documents for this query, we needed to visit all the documents. And the only reason we needed to do that is to retrieve the total number of documents that match the query. Here is another example, just to show you that it also works with multiple terms. So winter is coming. I'm looking for winter is coming on two fields, title and text. I'm using a tiebreaker of 1 just to ensure that the score of the matching term on title are summed with the score of the matching term in text. If I play the query, I can see that it's still quite fast, and compared to a query with track total hits set to false, we can see that the improvement is significant. Sorry, it's true. So here we see that something like 10 times faster. Thanks to the block max score that is enabled by default in Elasticsearch v7, we can now have a fast search experience where if you want to disable it explicitly, you need to set an option that is called track total hits. to true to retrieve the behavior of the previous version. The rule of thumb of this optimization is that term queries, Boolean queries, and phrase queries can skip non-competitive documents. So for the majority of queries, you will see something like a few percentage slower up to 1,000 or a few thousand faster queries, thanks to the fact that we can now skip blocks of document quite efficiently. So now that we have a faster search, now that we are able to retrieve documents efficiently, the top document efficiently, there are things that we couldn't do using the normal search that are accessible to this new optimization. So this is the case, for instance, for search as you type. So search as you type is something that needs extra fast search, because every time the user hits a keystroke, we need to execute a search. And so for that, in Elasticsearch, in the previous version of Elasticsearch, we have another data structure that is decorrelated from the main index and that uses an FST internally, so finite state transducer, that is optimized for prefix query. The downside of this approach is that because it's decorrelated from the main index, every completion query, so every query that tries to complete its input with document suggestion, cannot be mixed with any of the query that we have in our dataset. So it's not possible, for instance, to filter a completion query with a specific category that is coming from another field, even though the fields seem to come from the same index. So now that we have a faster search, we wanted to provide a new way to do this search as you type query. So we wanted to provide a new experience, a new fast search as you type experience that will also be flexible. Thanks to BlockMaxScore, we can now apply the same algorithm, so the same ID, to queries that retrieve the top documents, but this time in the context of a search as you type. So first, search as you type will need to handle infix search. So we will want to find queries that start at any position of the field. We also need to match prefix search, so terms that are incomplete, that should be considered as prefix. And all that, we want to do that directly in the inverted list of the main index of the Elasticsearch version 7. Since the design of this was made with MaxScore optimization in mind, we are confident that the performance for this new field type will meet the requirements that this kind of feature are. So this is available. This is not available in Elasticsearch 7.0, but will be available in 7.1, so the next minor release of Elasticsearch. Continuing the new features that we added in Elasticsearch v7 to make search easier and faster, I'm introducing here the feature field. So the feature field is an extension of the MaxScore optimization that allows to efficiently mix the textual score of your query with a static score that is extracted from the document. So say, think for instance of the page rank associated to the article, or in the demo case, the page view, so the number of unique views that an article has, regardless of the query that is on. In previous version of Elasticsearch, it's possible to use something that is called the function score, that we renamed script score, and that is very flexible. So you can do some silly things like combining your score with the page rank by multiplying. Of course, this is not a good idea, but since the solution is quite flexible, it allows you to do that. And this was one of the main source of difficulties, because we allow everything. It is difficult to know what is good and what is not good. So the feature field, and this is a very important distinction, will, at the cost of less flexibility, provide a solution that is based on the BM25 saturation to combine the score of the textual part of the query with a static score using what we call a saturation function. And the saturation function will compute a value between 0 and 1 based on the static value that is indexed within the document. Of course, all this wouldn't be possible if it wouldn't take into the benefit of the BlockMax scoring that we just mentioned. Let's switch to a small demo to just show what I just described. So here is a small query that is supposed to be representative of search as the type. So I'm using a multi-match query on the same index. I'm using a new type of multi-match query that is called bool prefix that will consider only the last term in the query as a prefix. So here my query is game of t, where t is considered as a prefix. I'm using the new search as you type field, which has multiple subfields inside. So the title field is the root field. It's just the normal field indexed exactly the same as the text field. It has a 2-gram field that contains the shingle of size 2 and a 3-gram field that contains the shingle of size 3. It also had a hidden field that contains the edge engram of the input, and that allows us to run efficient prefix queries on the field. So if I run this query, I can see that it's still fast, so it's less than 40 milliseconds to run a query where every term in the query is optional. So, so it could evaluate on all documents that contain T, that contains word in the title that start with T. Here is another example with a query that is Michael G. So here I'm looking for all the articles that talk about an individual that the surname that has a surname that starts with J. And as you can see, the contract is correctly. So the result is quite good in terms of matching. So I'm matching exactly the input, so Michael G. But most of the individuals that are here are unknown to me, so it seems that the relevancy is not met for this query. So this is where the wrong feature query comes in. And for the same query, I can mix a bool prefix query with a wrong feature query that will boost documents that have a big number of page views during the last week. So if I run the same query, one thing to note is that it's still quite fast, but the results are completely different. I'm sorry, I have a space here. The query are the results are completely different, and this time they return the correct individual, so at least the one that are the most famous in Wikipedia. Sorry. Since I'm running out of time, I will mention just very quickly the interval queries. So interval queries are a new family of proximity queries. I invite you to look at them as a replacement for span queries, where the main idea is to provide a better consistency on the way we match and score intervals for proximity queries. Span queries are known to be difficult to understand, and sometimes it is impossible to know if the non-matching of a specific span query is a bug or feature. With interval query, we introduce new semantics that allows us to ensure that there are some types of query that will be run in an efficient way while keeping the relevancy at a high level. And with that, I'm going to leave for the next talk to Yannick Welch, who will talk about cluster resiliency and scale.
Thank you, Jim. That was a great overview of the new search improvements in Elasticsearch 7. So what Jason and I would like to talk about are the resiliency and scale improvements that were made at the node level, cluster level, as well as for multi-cluster setups. And one of the biggest changes in this area is perhaps the new cluster coordination subsystem. So this functionality sits at the very heart of Elasticsearch, and it's what makes nodes work together as a cluster. It is one of the reasons why Elasticsearch has become so widely popular, as you can effortlessly scale it from just a small cluster with a few nodes to large clusters with hundreds of nodes. In order for nodes to work together as a cluster, the nodes need to agree on a common view of which nodes are part of the cluster, which indices exist, where the different parts of the data resides, and so on. And this common view among all the nodes in the cluster is called the cluster state. And its consistency is critical to the health of the cluster as it powers fundamental functionality such as data replication, searches, and more. The role of the cluster coordination subsystem is to establish this common view in the cluster and to coordinate updates to this view. Its core functionality can be roughly divided into 3 roles. First one is discovery, where it assists the nodes discovering each other to find an existing master or enough master-legible nodes to elect a master. Secondly, it manages the master election by establishing a particular node of the cluster to be the master of the cluster. And in a third step, this elected master node then makes sure that all nodes in its cluster receive updates to the cluster state. And it also makes sure that the cluster is resilient against nodes becoming unavailable or dropping out of the cluster. Elasticsearch versions prior to 7 used a cluster coordination subsystem called ZenDiscovery. And this subsystem has evolved and matured over the years and successfully powers clusters large and small. It comes with a few limitations, however, that we found difficult to address in the current implementation. Instead, we took a step back and based on what we learned through user experiences and support, we thought about what we could do differently if we were to redesign and re-implement this subsystem. So our goal was to make it safer, more flexible, easier to use, and performance scale even better. And while a feature like that has many behind-the-scenes changes for things that you typically expect just to work, I'll be focusing mostly here on the user-facing aspects. And the biggest user-visible change is perhaps the removal of the minimum master node setting. I'm sure many of you know that Elasticsearch requires certain settings to be properly configured before you go into production. And for versions prior to 7, the most crucial one is probably the minimum master node setting. With this setting properly, without the setting properly configured, a cluster that suffers a network failure is at risk of having the cluster split into 2 independent clusters, what we call a so-called split brain situation, which can and will lead to data loss. In a cluster of 3 master legible nodes, you would set minimum master nodes to 2, or more abstractly, to the number of master legible nodes divided by 2 plus 1. Unfortunately, we noticed that many users would forget to set this correctly, or they would forget to adapt the setting when adding or removing master legible nodes. And while everything looks fine on the healthy network, as soon as there are network disruptions or long GCs, there's a risk for split brain situations where minimum master nodes is simply too inflexible to provide a safe option to scale a cluster. For example, when shrinking a cluster from 2 nodes to 1 node. And while removal of minimum master nodes is probably the biggest user visible change, the new cluster coordination subsystem also brings performance benefits, with master elections now being much faster. So when discovering master elections in the old system at least always took 3 seconds, for example, after full cluster restart or master failover, Elasticsearch 7 typically just takes a few hundred milliseconds to do the same. So you will enjoy much shorter downtimes in case of a master failure. Besides making the new cluster coordination subsystem faster, we've also made it easier to debug configuration issues. So starting in 7, if a node cannot discover a master node or cannot win an election itself, then Elasticsearch will periodically log a warning describing its current status in enough detail to help diagnose many of the common issues. The new cluster coordination implementation, which is, by the way, also a fully new implementation, is also an engineering field. To develop this new subsystem, we have used formal methods, which are more typically used in the design and development of safety critical or security critical systems, for example, in the aerospace industry. Before writing even a single line of code, we created a formal specification of the algorithm and verified its safety properties using a model checker. The implementation has been checked using extended testing techniques and new test infrastructure, which simulates complex failure scenarios to check that the system behaves correctly, even under the most adverse conditions. This is critical because distributed systems like Elasticsearch must be prepared to deal with many strange situations. So nodes sometimes run slowly, they pause for garbage collection, suddenly lose power, and similarly networks suffer from partitions, packet loss, periods of high latency, or they may deliver messages in a different order from the order in which they were sent. And the testing framework covers all of these, providing high assurance as to the quality of the new implementation. This new implementation also addresses a very rare failure mode of versions prior to Elasticsearch 7, where repeated network partitions could cause cluster state updates to be lost. and this is now fixed. So as a reminder, issues like these are recorded on the Elasticsearch resiliency status page, so the one you see on the right here. This page covers the known resiliency-related issues in Elasticsearch and also tracks progress on the items that have been fixed. So feel free to check out that page for any resiliency-related updates. Finally, I would also like to mention that even though this is a fully new implementation and has substantial changes to the prior one, upgrading to this new system can be done without downtime. So just by using a rolling upgrade from 6 to 7. And while some of the settings have new names, many of the old ones work as well. So please use the Upgrade Assistant, consult the docs before the upgrade, and engage us with any questions you have. Finally, I would also like to highlight the blog post that we released a few weeks back, going much more into detail of the changes and providing more background material. So please check that one out as well. To summarize, so the new cluster coordination subsystem is faster, it's safer, it's more flexible, it's easier to use, and I'll now hand it over to Jason Teeter to present some of the other great resiliency improvements in Elasticsearch 7.
Hey, Yannick, thanks. As Yannick mentioned, we want to share with you some improvements that we've made to the resiliency and scaling of Elasticsearch. Yannick described for you some of the changes that we've made in terms of cluster resiliency and scaling. And I'd like to share with you some improvements that we've made along the line of individual node resiliency, as well as your ability to scale your use cases across multiple clusters. So we'll start by talking about the real memory circuit breaker that we've introduced in Elasticsearch 7.0. We've engineered Elasticsearch from the ground up to be resilient to failures of individual nodes. This comes about through features like replica shards and master failover. We've also engineered individual nodes with resiliency in mind so that they can sustain significant load from indexing and searching. For example, if you send too many requests or too large of requests to a node, Elasticsearch will push back. This is done via circuit breakers, which track memory usage of different aspects of Elasticsearch. The idea is that by estimating memory usage of a request up front, we can accept or reject the request based on how much memory is already being tracked for other ongoing requests and components of the system, such as Lucene memory usage. There's also a parent circuit breaker, which takes a global view over all circuit breakers. This lets Elasticsearch push back even if none of the individual circuit breakers are tripped, but globally too much memory is being used. It's impractical to track every allocation, and estimating the exact memory usage up front is not always possible. This means that prior versions of Elasticsearch took a conservative view of memory usage and overhead. While in these previous versions, circuit breakers provided some resiliency against overloading a node, they were a best effort mechanism, and it was still possible that nodes could frequently die with out-of-memory errors. This is especially problematic on nodes with smaller heaps, since the relative overhead is much higher. With Elasticsearch 7.0, we have significantly improved the resiliency of individual nodes by refining the circuit breaker mechanism to take into account the real memory usage of nodes when determining whether or not to trip the parent circuit breaker. By taking into account the real memory usage rather than an estimate, Elasticsearch is able to be far less conservative in its estimate of overhead. Individual nodes are able to sustain load and push back in more scenarios and die far less frequently with out-of-memory errors. Additionally, Elasticsearch is now able to classify when circuit breakers trip into two categories, whether the situation is permanent or transient. This information can be reported to clients when a request is rejected, so that the client can take this classification into account and determine whether or not to retry the request or to surface the situation to an administrator who can help resolve whatever issues led to high memory usage. We did real-world testing of the real memory circuit breaker, and the results are promising. Taking into account the real memory usage adds no overhead to the execution of a request. Based on our testing, this tracking adds less than a microsecond to request execution. We ran full text indexing workloads against nodes with small heaps. In older versions of Elasticsearch, the node would die with out-of-memory errors. With the real memory circuit breaker, the node can sustain the load and instead push back against the client. We also performed experiments with aggregations that intentionally produce a very large number of buckets. Older versions of Elasticsearch would die after a long period of painful attempts to garbage collect, but Elasticsearch 7.0 with the real memory circuit breaker can sustain the load and push back on the client. If you'd like to know more, please check out the blog post that's linked here, or check out our docs. And now I'd like to talk about some improvements that we've made that help you with resiliency and scaling Elasticsearch across multiple clusters. The ability to replicate Elasticsearch indices between clusters and data centers around the globe has long been our most heavily requested feature. After years of engineering effort and investment, we are excited to announce that cross-cluster replication is production ready. Cross-cluster replication is aimed at a variety of resiliency and scaling use cases. For example, for disaster recovery and high availability purposes, you can replicate indices to a disaster recovery cluster located in another data center or region. This gives your mission-critical applications resiliency to data center or region outages in your cloud provider. For scaling purposes, you can use cross-cluster replication to locate clusters in geographic proximity to your users. This helps you improve your overall user experience by reducing the latency that they would face while having a request serviced by Elasticsearch. Instead of servicing these requests across the globe, they can be serviced by local copies of your Elasticsearch indices that have been replicated using cross-cluster replication. Another scaling use case that is addressed by cross-cluster replication is to use cross-cluster replication to replicate indices from a large number of small clusters to a centralized reporting cluster for analyzing and aggregating events globally. For example, a large global bank might have hundreds of Elasticsearch clusters in branches around the world. And with cross-cluster replication, they can easily replicate these indices in these individual branches to a centralized cluster in a main data center. Prior to cross-cluster replication functionality being introduced in Elasticsearch, addressing these use cases required third-party technologies which carry significant overhead and expense. Now with cross-cluster replication production ready in Elasticsearch, you can address these use cases with ease. Cross-cluster replication is engineered around an active-passive index model. This means that replication is configured at the index level as opposed to the cluster level. There's not a notion of a master cluster, but rather a notion of leader indices, which you can have multiple following indices. This enables you to architect complicated replication technologies depending on your use cases. For example, you can have some indices replicating from a US cluster to a European-based cluster, and other indices replicating the other way from Europe back to the US. Cross-cluster replication supports newly created indices as well as existing indices that have soft deletes enabled. Soft deletes are new technology that we introduced into Lucene to enable Elasticsearch to have full control over when deleted or updated documents are purged from the underlying index. As Clint mentioned earlier, this technology will serve as the foundation of the Changes API, which will eventually allow you to have clients subscribe and be notified of changes to an index. Soft deletes are enabled by default in Elasticsearch 7.0, meaning that you can use cross-cluster replication out of the box. For time-based use cases, cross-cluster replication has functionality that enables you to configure patterns of indices to automatically follow. For example, if you have daily web server logs that you want replicated from another cluster, you can configure auto-follow patterns so that as soon as a new daily index with those web server logs is created, a new following index will automatically be created and start tracking changes from the leader index. Cross-cluster replication automatically replicates mappings and setting changes, which helps keep the administrative overhead of replicating indices to another cluster low. We have dedicated stats APIs for tracking the status of replication, which includes metrics that help you determine if your following indices are keeping up with their leader indices and gives you the insight you need to tune replication if needed for your use case. This endpoint also includes error reporting so that if following is interrupted, you will have the information you need to address the situation. Cross-cluster replication is able to classify errors into recoverable and fatal errors. Cross-cluster replication will automatically retry with backoff when it encounters a recoverable error, such as a network partition, and clearly denote in the stats API when it has encountered a fatal error that it cannot recover from and requires your intervention. We have also integrated cross-cluster replication with index lifecycle management, so that as leader indices are managed by index lifecycle management, the fact that there are follower indices is taken into account when performing management operations such as rolling over, shrinking, and deleting indices. We have also introduced into Kibana beautiful user interfaces, fully compatible in Kibana 7.0 with the dark mode that Dave mentioned. You can use this user interface to monitor and manage cross-cluster replication. These user interfaces enable you to visually track the status of replication, as well as configure remote clusters, follower indices, auto-follow patterns for the time series use case, and start, pause, resume, and stop replication. If you'd like to know more about cross-cluster replication, we have an introductory blog post and some docs that we hope you'll check out. And now I'd like to turn it over to Nick, who's going to talk about some of the geo functionality.
Excellent. Thank you very much, Jason. At Elastic, we've always had the primary objective to make very complex use cases as simple as possible. And Geo is no different. The way we view Geo in the grand scheme of the entire Elastic Stack is just another data point. You should be able to plot your Geo points, your Geo shapes on a map, index them, search them with ease. We've seen in the past with the 5.0 release some performance improvements for Geo points, but also not just performance improvements, but also improvements in the mapping ability and the ability to specify Geo points as just another data point. It used to be that you needed a GIS PhD to be able to specify these parameters. We wanted to lift that barrier of entry for all of our users and provide a way to specify these fields very simply just by saying, I want a Geo point. Geo shapes are no different. We've spent the last version and a half really trying to refine this capability and this ability, not just inside the Elasticsearch mapping ability, but also down at the Lucene level. So I'm proud to announce, as of 7.0, we are fully switched over to the BKD-backed Geo shapes. I'll touch a little bit on the performance improvements, as well as give you a quick demonstration of how to specify these, what has changed in the mapping and how to specify these Geo shapes. I'll also touch on some of the other features, including a new aggregation that we would like to present that's now available in 7.0. And then I'll hand it over to Thomas, who's going to give you a demonstration overview of all the amazing capabilities that has been added to Kibana for the mapping application. If you haven't used Elasticsearch for Geo before, or if you have, like I said, we want to try to keep things as simple as possible. Being able to designate a GeoShape field should be no different than just specifying an integer or a date timestamp. And that's what we've strived for all along. And I'm happy to say 7.0, we're here. As a quick demonstration of this, you can now specify a GeoShape field simply by defining its type as geo_shape. In the past, we required you to know quite a bit about the indexing strategy under the covers. So if you looked at the documentation or you tried to use GeoShapes in the past, it was probably very confusing to read through this litany of parameters that we required. We also spent a lot of time internally trying to reach appropriate defaults that would be common for the general user, that made it very complex for a more advanced user to go in and make changes to the index parameters. Happy to say all that has now gone away, and we can now specify these GeoShapes like any other field. So what kind of performance do we bring in addition to this ease of use? Quite a bit, and I'll show you some of the benchmarks that we were able to see on the Lucene level here in a second. In the past, a very simple 1 degree by 1 degree shape, as seen here, with a total of 8 vertices, would use up 1.1 million terms in the inverted index, which, as you can see, for one shape would cause a computational explosion in the index side. With the release of Lucene 7.6 and now Elasticsearch 7.0, we were able to reduce that index size down to a total of 8 terms. With that, in order to achieve this, what we've done is we've switched from what we call a raster, which is the cell base that you see on the left, into a vector-based indexing strategy. And that allowed us to achieve precision improvements as well. In the past, you had to designate your spatial size for each of these cells. You no longer have to do that in 7.0. What we've done is we've achieved the ability to index all shapes at approximately 1.11 centimeter precision. So you no longer have to determine or make a determination or a choice up front in terms of what kind of spatial resolution you want. It will all operate at the same resolution, regardless of the size of your shape. As a quick example, we've taken some of the southern states here, and we've run through the vectorization process, which is also in Lucene world, or technical speak, is known as tessellation. So we've taken shape files, we've taken a number of GeoJSONs that represent all the vertices of these shapes, we've passed them in, and we've achieved a substantial performance gain on not just the indexing, but the indexing speed, but the indexing size. These performance gains can be seen in this chart right here. What you see prior to the 7.0 release on index size is we are now getting closer and closer to, for shape indexing, we're getting closer and closer to the same index size as just for single points. This is pretty mind-boggling, considering a single point is just a single record, yet shapes can be decomposed into a set of terms. But as you can see from the first example here, we've moved again from 1.1 million terms down to a simple 8. So it's not hard to see that kind of compression being achieved inside the index. And with a smaller index size comes a faster indexing performance. This graph here shows a extremely large jump on the far right side, where the purple is the indexing speed for shapes. the very top line, which is light blue, are our points. So you can now see, as of the 7.0 release, indexing shapes takes no longer than it used to take for indexing points. And with some of these improvements, not just to the shape indexing, we made improvements to BKD in general. So these same performance improvements will be seen inside of not just your point data, but also inside your numeric IP and date fields as well, since they all use the same data structure. What are we hearing in the community? Well, quite a bit of feedback. We did release this, an early release of this inside of Elasticsearch 6.6 for some of our customers and users to begin playing with it. Of course, 7.0, it's now converted over to the default. And not just internally, but our customers in general are coming back with quite a bit of performance improvements and substantial and really exciting feedback here. In one instance, we had a single shard that was consuming 16 gigs of heat and on a single shape running for 4.5 hours on the previous inverted index approach. It now takes less than 1 second to index that same shape. Customers are coming back who were using pre-6.6, pre-7.0 Elasticsearch, and they're seeing the performance gains of 25 to 30 times faster, not just in indexing, but also on the search side as well, along with the substantial index size compression and improvements. And in addition to that, all at 1.11 centimeters spatial resolution. Not just on the indexing side, but on the analytics and the analysis side. We've made some improvements or added an additional aggregation that allows us to better visualize inside of Kibana. Happy to announce a new aggregation called GeoTile Grid aggregation. Formerly, our GeoHash grid aggregation was the way that we would visualize thematically on Kibana in terms of a heat map, geopoint data in terms of a heat map. This didn't work out so well because the way that you actually encode geohashes does not easily align with the Web Mercator specification, which is the specification that primarily almost all web mapping applications use. With the GeoTile Grid aggregation that's now available in 7.0, we're happy to say that all your geopoints will now nicely align with the Web Mercator map tiles. So if you have your own mapping application and you're not using specifically Kibana, you can use the GeoHash tile, the GeoTile Grid aggregation now and align with almost any one of your mapping feeds or WMS layers. That's now available as the default in Kibana 7.0. So I would like to go ahead and hand it over to Thomas to give you a demonstration of our new mapping application available in Kibana.
Thank you, Nick. So I will talk a little bit about what we've been doing on the front end in Kibana to actually visualize the geodata that you would have in your Elasticsearch clusters. And in 7.0, we're introducing a beta of the Maps application, which is a dedicated application for visualizing and analyzing your geodata. There are a couple of new introductions that go beyond the mapping features that we already had in Kibana. And I'll just outline them here. I'll also show them in a demonstration right after this. The biggest addition there probably is that you can compose a map from multiple sources. And these sources can really come from anywhere. They can come from your Elasticsearch, so your own business data in your clusters, but also from third-party providers, or if you're hosting your own geo services from your own. And I'll demonstrate that as well. Another introduction is that users are now able to visualize individual documents on a map. So if your document has spatial information associated with it, you can plot it as is. That was something that was not possible before in Kibana. And all these layers, regardless of where your data is coming from, can be styled on the client using styling rules. And these styling rules can either be static or they can be driven by properties of your data. And I'll show that as well, how that works. And then I'll call this out as we do provide out-of-the-box mapping. So we have something called the Elastic Map service, which provides a standard set of geodata that is useful for a lot of use cases. So like a world-based map, administrative boundaries of countries. The idea there is that you can take that data as is and just get started with it and mash it up with your own data. Also, maybe interesting to call out is that, so Nick mentioned that a lot of users used to have a background in JS to be able to work with these tools. We think that's not necessarily a requirement. A lot of data has geo component. And so for all these other use cases where location is important, they should just be easy to use. So if you're already doing log analytics or application performance monitoring, adding that geo component to it, adding those maps to it, and exploring your data on a map should be easy. And you should be able to do that right now with the Kibana, basically. With that, I'll go into a demo. So I have a feed running on my computer. It's actually producing synthetic data, but I think it'll illustrate the purpose of Suricata events. Suricata is a data model for network traffic monitoring. And basically, a document is very similar to what it looks like here. And so what we'll do is we'll create a map to basically track this network activity in Kibana. So let's go to the Maps application. And we'll just start by adding a layer. So what we see here in the background is that background layer that the Elastic Map service provides. So we have a getting started experience, but now we'll start adding our own data. And we just want to get an overview of that data that we have. So let's just bring this in and just kind of get a sense of where it is. And what we're interested in is in the provenance of a network request. So we'll map the source location. And since this is for an overview layer, we can kind of take a look at it in different views. So here as a grid, for example, is using this geotile grid aggregation. But what we'll choose is a heat map because it looks a little bit nicer. So we'll add this to a map, and we can call this request overview. We'll make it a little bit more fine-grained, so our heat map is a little bit more detailed. So we get an overview of where our requests are coming from, and we can immediately see that apparently in Europe, this is where most of our requests originate. And this is one way of looking, sort of getting a global overview of our network traffic, but we can also maybe create a more thematic map. And very common, these kind of maps, you want to see requests by some sort of boundary that makes sense. So we want to see our requests now by country. So what we can do is we can then bring in the country layer from the Elastic Map service, which it also hosts all these other country boundaries. But let's look at world countries. And so right now, this is a very unusable map, really. It's just an outline of the countries. So, but what we want to do is we want to enrich this information from the Elastic Map service, in this case, the world countries, with our own data, our network traffic. So what we'll do is we'll join this country data to our incoming network request. And what we do here is we basically use a key field, an ISO code, which identifies a country, and join it on the client to the corresponding code in our index. This is something that code is produced by the GeoIP plugin that you can use when you are ingesting your data. So if you're interested in the provenance, now this information becomes available to drive our styling. So now we want to symbolize our countries based on this metric. I will keep it simple. This is just the number of requests. We might want to move this to the background. So now we have a different global overview. So we have the global overview based on just really where it happens. That's our heat map, but then also by country. I showed bringing in data from the Elastic Map service, but you don't necessarily have to do that. You can also bring in data from your own services. So say that we want to replace this background map with our own. We can use basically a couple of services. We'll stick with the tile service, but if you have WMS services, that will work as well. So this is a dark map that maybe is a little better for our use case. Also works well with the dark theme. This is a third-party service. I just wanted to illustrate this concept, but the Elastic Map Service, we are working on actually providing a dark theme out of the box as well. And, let's scroll this back up. Move this to the bottom, so it's not hiding our data, and we'll hide the other layer. So our map is starting to come together, but what we're really interested in telling is the entire story. So what we're showing now is only the origin of our request and grouped in different ways. But what we also want to show is how this is actually interacting with our data centers that are responding to this request. So we'll bring in the destinations as well. And here we'll just retain the bubble styling. Data centers. That's maybe just because we're symbolizing a different metric altogether. Let's just change the color so it doesn't conflict with our countries. Maybe increase the transparency just a little bit so it does not blend together too much. And so now we actually see which data centers are responding to the most. And we actually see this update in real time because we're just looking at the last 15 minutes now. What I wanted to show now too is I've shown sort of the roll-ups, the aggregations. But we can also plot individual documents, so the actual individual request that is happening. So let's do that for our source location, so where the requests start. And we can also pull in what data we actually want to see, and maybe we'll just, in this case, interested in the start date and maybe the city where it's originating. So we can see this on our tooltips. Since these are individual documents, we don't want to see everything so big, just like make it smaller so it's not cluttering too much, as small as we can. So now we have basically the global overview and also the details if we are interested in those. The last thing that I want to bring in is actually a trajectory of these requests. So this is something new as well in Kibana, is the ability to visualize any geo shape. And so what our ingest pipeline is keeping track of is the actual request path, which is a line. And so we will make that map as well. And we'll call this path for the request. And we'll symbolize it with something that might be useful for an analyst and the duration of the request. The assumption here is that requests or connections to our data center take a long time. It's something that we might be want to investigate. So let's style the border color based on the duration. And we can actually do that for any property. So that maybe the width we want to be driven by this property as well. Let's actually make this usable. So now our map is starting to come together, and I think this is a sort of an overview of the last 15-minute network traffic that we're having. But this is Kibana, so that means that all the search power that we have in Elasticsearch, we also have available here. So let's make this a more up-to-date kind of view, and we're just really interested in the last 5 minutes. So now our entire map changes just based on the last 5 minutes of our traffic. And we might want to have this refresh every 5 seconds as well, so that we can bring this up on a dashboard and basically just have it up in our control center. So now our data is updating every 5 minutes, and so we can kind of keep track of this. Since this is global data, it's starting to get a little cluttered. So if you're interested in actually performing a search, you can do that as well. So you could say, let's just focus on our data centers in So now we only see basically requests going to that single data center. You can change this on the fly. So what other data centers do we have? Los Angeles. And maybe that's why we're interested in this map. So our network traffic up to date for the last 15 minutes to Los Angeles, updated every 5 seconds. What we can do next is actually maybe just make this full screen. And now we have a map that we can bring up on a display. So that's what I wanted to show about the Maps app. I think there will be time for a Q&A right now. So I'll hand it back over. Thank you.
That's excellent. Thank you, Thomas. And thank you for all the presenters. I think we've got a lot of good engagement in the live chat here and a whole bunch of great questions that popped out. I realize we're running a little bit late in terms of the timing, but I think we can take just a couple of questions here and then continue to follow up in IRC afterwards. Maybe a couple of questions. There were a couple of really interesting ones that I think are worth highlighting. One of the important ones, I think, for Jason Teeter, when will the improved circuit breakers reduce the occurrence of long garbage collections and make individual nodes more stable, more resilient, and so forth?
Yeah, thanks, Steve. That's a great question. The short answer is yes. It will help reduce the likelihood and pressures from garbage collection. The idea is that when an Elasticsearch node is nearing its limits, rather than it behave as it did in the past, which is attempt to service the request and allocate more memory than the node might have available, and therefore enter long and intense garbage collection pauses. By tracking real memory usage, we're better able to see how close we are to the limit and therefore reject these requests before we start to spiral into these garbage collection death cycles. And so, yes, we will be less likely to succumb to intense GC pressure than older versions of Elasticsearch.
That's great. That's great news for everybody, I think. The more we can make individual nodes stable, the more stable an overall cluster is, which is a good thing, I think. One of the other questions that we had for Jim was, do you need to make any changes to your indexing approach, or is there any index time overhead to take advantage of the performance improvements from the weak and or the BlockMax wand work?
No, and I think that's the beauty of it. You don't need to do any reconfiguration of your index. The only thing that you need to index this new data structure into your index is to make sure that you reindex all your document into a newly created index in the V7 version.
Got it. That's great news.
And the amount of data that you store, Jim, is minimal, isn't it?
Yeah, exactly. It shouldn't be. It shouldn't slow down indexing at all. At least that's what we see in our benchmark.
That's right. If you see something different, let us know. That's great. That's really great news. One question for Nick. When you're searching for points within a geoshape, are we using a min bounding box approach, like drawing a square or smallest square around an area and then just saying it's in the min bounding box, or are we getting accurate results, like more accurate results when we're doing this sort of point in geoshape query?
Yeah, that's a good question because it hits on the way we used to do it. Prior to the 7.0 release and BKD-backed geoshapes, we used to do basically a two-phase where we would first search the bounding box and then we'd have to go through a post filter iteration process, and that part would be extremely slow. With BKD-backed geoshapes, we don't have to do that anymore. We actually get accurate down to the 1.11 centimeter right off the bat without having to go through that two-phase process. So that's also what helps speed up the query performance. So thanks for that question. Helps clarify how we were able to achieve some of these performance boosts.
Well, that's really great. And maybe 1.5 more questions. So one question, I think this is probably for Jason Teeter. For cross-cluster replication, does the follower cluster need to be identical or roughly the same size as the leader cluster? What are the dynamics in terms of the follower cluster relative to leader cluster? Yeah,
that's another great question. The short answer is it depends. The long answer is that it's really going to be based on your use case. For example, if you're not replicating all of your indices, then the second cluster would not need to be sized the same as the first cluster. If you've got some large cluster that has only a small number of indices that you want to replicate elsewhere, then you can get away with your second cluster being much smaller. On the other hand, if you have a use case where you are aggregating a large number of small clusters into a centralized cluster in a main data center, then your cluster that you're replicating into would need to be large enough to accommodate the indices of all of those small clusters that are spaced around the world. So it really does depend exactly on what your use case is. And ultimately, you just need to size that second cluster based on the indices that you're replicating there.
Yeah, that's actually great information. So it's sort of like, think about the amount of data that will be going into the follower cluster and size it according to that, in the same way you would size your production cluster in some senses.
Yeah, exactly. It's just a secondary sizing exercise that you have gotten used to on your primary clusters.
That's great. Okay, so maybe the last question, this is a good one in the chat. Will there be more blogs, webinars that dive deeper into some of these features and some of the other features we didn't get to dive into? Yes, there will. So stay tuned. There will be a lot more content coming from us, and we'll try to do our best to include lots of links and follow-ups for some of the existing material on these features as well. So again, on behalf of us here at Elastic, thank you so much for joining. We really appreciate you taking the time out of your busy day to come and join us. And thank you very much, and happy searching.